Hello and welcome back. This is lectures 3 of Systems 556, 750, Simulating Neurobiological Systems, as part of the University of Waterloo course taught in the fall term of 2021. Okay, what's happening now? In the last lecture, we talked about an individual neuron. Now we're going to talk about how groups of neurons might work together to represent information. What might that look like? Where are we going to go with that? I'm going to start with a reminder of a couple videos that we saw on the first day. And what I'm trying to establish here is that neurons do represent information. What do we mean by that? I mean that there's some sort of correspondence between something in the outside world and the neural activity. And that's sort of the bare minimum that you might want to say for neurons that represent things. So, what that might mean. In this particular experiment, we've got we're recording from neurons in the visual cortex, and this is the classic human weasel experiment where this sort of stuff was sort of established, that neurons do represent things in the visual cortex. And what we're showing here is, on the screen, is what's being visually presented to, in this case, a cat. And we're moving this bright dot around. And hopefully you can hear in the background a bit of clicking sound. That's the activity of the neuron. And what they're trying to do is they're varying the visual stimuli and trying to figure out what changes in the visualized stimuli cause this neuron to change its activity. So there's some sort of mapping from visual stimuli to the activity of the neuron. Fine, that's okay. That's sort of the classic situation that was sort of started this whole way of thinking about neurons as representing information. Of course, it's got much more sophisticated since then. We also showed this example on the first day where we're recording from a bunch of different neurons in the rat hippocampus. And what we end up finding there is that neurons at different, as the rat moves around in the environment, different neurons start firing. Okay? This is a much more complicated relationship between something in the outside world and the activity of the neuron. Right? And the sort of the visual one, that's sort of, we've got this sort of mapping from the visual stimuli to neural activity. But here we've got a situation where it's a mapping of, there's no direct sensory stimuli that tells you what location you are at. Something more complex is going on. Something inside the brain is allowing the rat to keep track of its location. And these neurons seem to be involved at least in representing that information. Okay. Again, as a reminder, what we're seeing here is the different colors are different neurons, and we're just sort of putting down a little dot wherever the rat is at the time when that neuron fires. You can sort of see these clustering of, oh, hey, look, this neuron seems to indicate something about being in this location. This neuron seems to be indicating something about this location. But it's also a pretty complicated code. So we've got to figure out, how can we quantify this? How can we figure out what it is that neurons are doing in order to represent this stuff? And this is going to be sort of the groundwork, the foundation of an assumption. This would be the first sort of main assumption that we're going to be making in this course, is that a lot of the times we're going to be having groups of neurons working together to represent something. So we tend not to have a single neuron representing a single thing. Instead, we're going to generally have groups of neurons that are going to work together to represent values. And we're going to put in a couple new things here. We're going to say that representation, we're going to put some constraints on it. In particular, we're going to say there's a nonlinear encoding of values, but a linear decoding of values. And this is going to be sort of our first sort of weird assumption we're going to be putting in order to sort of establish this quantification theory that we're trying to build up of how brains work. Okay? So we're going to start with this, see how far we can go. And first we've got to figure out what the heck we mean by these terms. All right. So what do we mean by encoding and decoding information? So let's start with codes in general. The idea of taking some value that I want to represent, and we're generally going to be using x to be the value that I want to represent. Okay. And there's going to be some function that maps x into some other thing that's going to be representing x. Okay. In this case, we're calling it a. In our particular neural case, it's going to be neural activity, which is why we're using a. So, but we've got something in the real world, we've got some value being represented. In the visual case, it was, say, some, here's the vision, the image coming in, that might be x. And a is going to be a bunch of neurons. One of the neurons might be the one that was being recorded from there, but there's also a whole bunch of other neurons that are also encoding things. So that visual stimuli is going to be encoded into the activity of a bunch of neurons. Just like, so, I don't know, in the sort of international flag alphabet, we have a different, each flag indicates a different letter, right? We're trying to represent a letter, it gets mapped into presence of flags. Morse code, we're trying to represent letters, they get mapped into dots and dashes. Okay. And if it's a lossless code, the first sort of definition, so we need some way of encoding information, but that encoded information is useless unless you can decode it. So you need some inverse function that is going to be taking your encoded information and turning it back into x. And if this inverse is perfect, if there is an actual perfect inverse, then we call this a lossless code. Right, sort of vaguely makes sense. Let's go with a slightly more detailed, worked out example. Let's go with binary numbers. And this is actually going to be an example of exactly what we're going to end up with neurons, in that there's going to be a nonlinear encoding and a linear decoding. If I go back here, whatever the heck it is, these functions that are mapping from x to flags or to dots and dashes, yeah, those are both wildly nonlinear, both the function itself and the inverse of that function. Those are just wildly nonlinear functions. There's no, you can't write it as some simple matrix math. What else are we going to do here? But it's going to turn out that this binary numbers situation is going to be something that we can write in terms of the same format that we're going to be using throughout the rest of this course. But hopefully this might be an example that people are sort of familiar with. So binary numbers. I have the number 7, and I want to represent it as zeros and ones, because that's all computers can do. And what we do normally with binary numbers, so if you have, so if you have the number 5 and it gets turned into 0, 1, 0, 1, a bunch of zeros, this is going to be a situation where we can do, all right, we could write what the math is of converting x, our number, into a sequence of activities. In this case, the activities are either ones and zeros. This is it's not quite intuitive what exactly this math is saying here, but you can sort of imagine what's happening in order to figure out exactly should this value be a 1 or not. Right? We could write out the math of switching from a scalar into a binary number. Doesn't really matter what this math is. The only thing I'm highlighting here is this is an ugly function that is doing some sort of mapping, but I don't really care what it is. It's just something that is going to convert into my activities. Okay. But then once it's in this activities, the zeros and ones, we're going to need to convert it back into x somehow. And in this particular case, with these binary numbers, this is a linear decoding. What do I mean by a linear decoding? Well, if I've got a sequence of zeros and ones, right, you multiply. So if you start with the digit all the way on the right, the digit on the far right means 1. And the next column is the 2's column. The next one is the 4's column. The next one is the 8's column. Right? What you're doing when you're decoding that value out is you're saying, all right, if the activity, if the value is a 0, do nothing. If the value is a 1, multiply it by 2 to the I. So multiply it by 1, or multiply it by 2, or 4, or 8, or 16. Right? 1 times those values will give me 2, 1, 2, 4, 8, 16, whatever. And then I add those all up, and that's going to give me my original value. Okay. So we've got this sort of this activity, and we're multiplying it by some matrix. In this case, it's the matrix of powers of 2. And that's converting from our binary representation. So, you know, maybe if we're representing the number 5, this is going to be 0, 1, 0, 1. Am I getting that right? Yep. No, definitely wrong. Number 5, it's going to be 1, 0, 1, and then 0, 0, 0, 0, 0. All of those zeros are going to be multiplied by zeros. The only things that's going to be left is the 1 and the 4. 1 plus 4 is 5. So we decoded it. Okay, so fine. I'm writing this in a really weird way. No one talks about doing binary numbers in this sort of format. But I'm just pointing out that this idea of taking some sort of internal encoding and multiplying it by some matrix in order to get a value out is something that we actually already do in other cases. Okay. We're taking a value, we are encoding it in a bunch of bits. You can sometimes call this a distributed code, and then we can decode that value perfectly fine. This particular code has some weird features. So for instance, it's not particularly robust to noise. If I add random values to my activities, you know, if I just have a small probability of each of these sort of flipping from 1 to 0, that could have a giant change to my code, my value that's being decoded out. Fine. I mean, it all depends on which ones flip. If these ones, if these bits over here flip, all right. Fine, probably doesn't have a big impact. These ones down here are going to have a huge impact. So it's not a particularly robust code if you have noise. So it's probably going to be the case that brains are not going to use this particular encoding. In fact, brains maybe don't even use a lossless code. Instead, brains are going to be, perhaps we're going to expand this. This might be a lossy code. It might not be a perfect representation of something. X in general, if X is sort of a real number, there's a lot, like, you know, how many decimal places are being encoded. Like, there's a lot of information that need to be encoded there. We might not be able to represent the value perfectly. We might have some sort of approximation. So that's the first thing we're going to relax, is instead of the decoding being an exact inverse of our encoding, we can say it's some other function that at least gives you an approximation of X. Okay. Again, this is something that's really, really common out there. Pretty much all audio encoding schemes are doing something like this. Another thing that might have come up in your other courses is taking a value, encoding it with its first few principal components using principal components analysis. Right. You're encoding it with a very small amount of values in a way that can be decoded back out with minimal loss of information. And this is going to be the approach that we're going to use for neural representations. All right, so maybe that sort of vaguely gives us the mindset that we're thinking about. How are neurons actually doing this sort of stuff? Well, the great thing is neuroscientists have been measuring from neurons for ages, and they've been doing exactly those sorts of experiments that I was showing of go vary something and see how the neurons change their behavior. So, for example, here on the left, I've got data from, I guess this is auditory or various different auditory areas. Each of these lines is a different neuron in a different part of the brain. And what we're varying is the sound intensity. Right? So sounds, different loudnesses. You go and measure from this, you take one particular neuron you're recording from, go modify the sound intensity, and you go see what it does. And okay, and we get curves like this. So fine, there's a neuron that, all right, seems to change its activity as the sound gets louder. Fine. Another part of the brain, I might have a neuron that does this. Fine. Another part of the brain, we're here. Cool. All of these neurons seem to be somehow encoding sound intensity. And this is the sort of data that you can easily find in, well, not easily, that is often presented in papers. So that's a sort of a common thing to see. You might also see things like orientation selectivity. So I have a rat running around in a maze, and I've got a neuron, depending on what my orientation, no, actually this is, no, sorry, not running around in a maze, this is lines at different angles. Right? I show lines at various different angles at the same sort of spot in the visual field, and I see how much this neuron fires. And we go, oh, okay, here's a neuron that fires. It fires a lot if it's a horizontal line, fires less if the angle, as the angle changes. Okay. Another very common thing that you'll go see in biology. And there'll be other neurons that are sensitive to other points, or to other orientations. Same way in these sorts of brain areas, we're only showing one sort of canonical neuron. You're going to find other neurons that have other sorts of curves. Okay. To give sort of another example of that, sort of what we might see as sort of a variety of neurons. So here we're measuring 3 different neurons in the same brain area. And in this particular case, these seem to be neurons that are sensitive to how fast the animal's running. Okay, so that's what's varying across the x-axis, is how quickly it's running, and we've got this one neuron here where it sort of sits there, fires at some constant rate, and then okay, as you're running faster and faster and faster, the neuron fires more. And this one here, as you run faster, this neuron fires less. Also a pretty common thing to find. And here's another neuron where, okay, it fires more most at this particular speed, fires less on either side of that speed. These are typical sorts of curves that you will find, that people measure when they go ahead and look at the real brain. Okay. Well, in this particular case here, we also have some nice data showing what the distribution is. So in this particular one little brain area, we have 4 neurons that prefer a low, a low firing rate. So that would be, so this neuron here is a neuron that prefers a low firing rate in that it fires more. Sorry, prefers a low speed, a low running rate. So this neuron prefers a low speed because it fires most when we have a low speed. This neuron prefers a high speed, fires most when we're going at a high speed. And then these neurons have some particular preferred speed in the middle. And that's pretty typical things to find. So this is what we're trying to sort of quantify. Now in the last lecture, we were making plots that looked kind of like these. Right? We were making plots like this one here at the bottom, these response curves. Okay, I have an individual neuron. We have some model of an individual neuron. I'm feeding current into the neuron. As I change the current that goes into the neuron fires at a different rate. Okay? And there's sort of, all right, there's some sort of similarity between these two plots. But we got to be careful here, because on the x-axis on this plot here, this is current. All right? Whereas on these plots, this is some value being represented. Okay? Terminology, these things down here where we're talking about just the actual response of a neuron, these are called response curves. Whereas these things up here in the literature tend to be called tuning curves. So what is the tuning of the neuron in that, how does the neuron's activity vary as a function of something else? Okay? And it might be some external stimulus, it might be some motor action that it's making, just something else. Okay. So if we want to sort of relate these two things, well, one thing we could do is we could say, okay, well, look, each of these neurons, there's some neuron model going on there. Okay? There's some actual neuron model happening, or there's some actual neuron. There's current flowing into these neurons. That current must somehow be dependent on whatever this value is. Okay? We will get to later in the course how in the world that current can show up. But we're just going to start with, all right, there's some relationship between this value being represented and the current flowing into the neuron. Okay? And if we quantify that, then we can relate this curve to this. Okay? So another way to write that is over here. We had the activity as some function. So this is my neuron. So I'm using capital G to refer to my neuron model. Again, it's whatever it is. Leak, integrate, and fire. It could, G could be a giant, huge numbers of, huge amount of computation, some really complicated neuron model, or it could be a really simple neuron model, like we're showing here. And this is a function of the current flowing into the neuron. We want to turn this into the activity as some function of X, right? Because we want to use this for encoding information. Okay? So we need some way of relating X. So for a given value, well, how does that turn into current? Okay. Each individual neuron is different. Each individual, even if each neuron has the same type of neuron, if each neuron has a different curve, that's going to mean each neuron has a different mapping from X into J. So that's why we've got a little J sub I here. Okay. So what sort of functions can we do for this mapping X to J? Well, if we try to take a look at these, there's some pretty simple functions we could start with. All right. Like we could start just by saying, all right, if I've got this curve, and I just sort of scale it up and down a bit and shift it left and right, I can at least make it stab at mapping these to these things. Right. So that's all we're going to do as the simplest possible thing that we might want to do to try to do this mapping. We're going to say, all right, we've got this X, we can scale it. All right, that would, scale it up and down. That could adjust this slope here. Okay. And we can shift it back and forth. Okay. It's going to be a somewhat complicated relationship going along here. But this sort of mapping should let us take this curve and shove it around to turn into this curve, these curves. All right. So that gives us an initial stab at how we might want to convert these things together. So we're going to have this sort of relationship between the current flowing into the neuron and the value being represented. Okay, and that works pretty well for these sorts of neurons. Doesn't work for everything. All right, well, it's going to work fine for this sort of thing. We can imagine it working fine for this. All right, I mean, that's just exactly what we built here. All right. Fine. What about this bottom one, or this middle one? This one where we've got the decreasing with X. Well, that should be fine as well, as long as we allow, there'd be two ways we could sort of think about this. We could just say, well, hold on, if this gain is negative, all right, then that would say that X times that gain would be a negative number, and then at the bigger X gets, the more negative it would get, and so the neuron would fire less and less until it finally stops firing. Right, we can kind of imagine that happening. Instead of allowing gain to be negative, we're going to do something slightly subtler, which is going to simplify life later on. we're going to say, look, this gain factor, that's much more about telling us how sensitive this neuron is. Let's keep that separate from this sort of more fundamental idea of, does this neuron like positive numbers or does this neuron like negative numbers? Right? Those are sort of just two pretty separate concepts. Let's not combine them together into one variable, this alpha. So instead what we're going to do is we're actually say, well, look, we're going to constrain alpha always to be positive, but then we're going to add in another factor, e, and in this case that e can be either be 1 or minus 1. Okay. And that's going to get multiplied by x in order to say, okay, if e is 1, that's going to be all the neurons that prefer larger numbers, because if e is 1, as x gets bigger, this whole value is going to get bigger, so this neuron is going to fire more. Okay. All the neuron models that we looked at, as you increase current, the neuron's going to fire more. And then for e is minus 1, then all right, as x gets bigger, this term is going to get more and more negative. It's going to get smaller and smaller. Eventually, the neuron's not going to fire at all. So that's always going to be just these decreasing neurons. Okay. Math-wise, we could have just combined these parameters together, but into one variable. We're going to keep them separate because it's going to simplify a lot of things later on. All right, so we can sort of believe that we can cover these two cases. And what about this third case? What can we do to this equation to make this happen? All right, just to get some sort of sense of what the problem is here. Well, G is like all these neuron models we looked at are generally of the case where as you increase J, as you increase the value being fed into them, they fire more. Okay. So we need some way of modifying this function, or this part of this equation, such that when x is near some particular value, that's where it gets its largest value. That's where this whole function gets its largest value. And as you get farther away from that preferred value, then you get less and less. That's a little weird. We're going to need some sort of similarity measure. Right, so we can sort of imagine it down here. Right? We've got some similarity. We're going to use the same variable e. So in these particular cases, there was something saying, all right, hey, look, we like positive numbers or we like negative numbers. Fine, it's sort of in that same family. We're going to some sort of similarity measure, but we just want to be able to generalize that to be values in the middle too. Okay. And I'm going to put in an extra constraint here, because there's tons of things I could come up with that could be this function. I want to put one extra constraint on myself here, and that is, I want this to be something that's easy to compute. Because eventually I'm going to need to say some sort of story about how the heck neurons could compute whatever the heck it is that we're doing here. Okay. And at least with what we have so far, all the math that's in these things up here, these are all things that I'm pretty sure neurons can do. I'm pretty sure that if I have current flowing into a neuron and then I have other current flowing into the neuron, then we can add currents. Like that seems okay. I'm pretty sure that if I have some sort of scaling factor being applied there, right, then it'd be like, oh, okay, I just make the connection into the neuron less strong, right? Like I can imagine how I might get into implementing this sort of addition and multiplication. I don't want to do much more. Right? We're going to have to, and we will in a couple lectures, say exactly how neurons would go ahead and do this. But I don't want to push myself to do anything too particularly complicated here. That's just going to complicate my life. So what else can we do here? Well, this is going to be a little bit weird. But one interesting thing, even though I've been plotting all these plots here where the x, this thing being represented, is a scalar, all these plots, and in a lot of the papers, the plots are scalars. There's nothing that says a neuron has to only be sensitive to one thing. All right? And indeed, there's tons of data out there that neurons being sensitive to multiple things. So what if X is a vector? Well, there's a simple similarity like sure for vectors, and that's the dot product. All right. If you take two vectors and you do the dot product between them, so that's taking all the elements, each element, multiply them. You multiply each element together and add it all up. That's the dot product. Notation-wise, we're going to be using this angle bracket notation, which may be unfamiliar to a lot of people for the dot product. The other common thing for people to do is put a dot in between the x and y, and that's the dot product. Same thing. We're going to be using angle brackets here. Anyway, but that's the computation. And one way to think of that as a similarity measure is that the other way to write the dot product is to say, okay, if x and y are vectors, what's the cosine of the angle between the vectors times some normalized times the length of the vectors? It's going to be what our value is. This thing is going to be maximum if x and y are the same. So what's that going to mean? That means that I might be able to get away with this for an equation. Okay. X is my value being represented. EI is the preferred direction in that space. We're going to have the dot product between these two things times our gain plus our bias. That's going to give, and then that's going to give me the total current. That's the current that's going to be fed into the neuron. That's going to give me my activity. Okay, that's a little weird. What's going on here? Fine. We're going to need to constrain this a little bit more. So one extra constraint we're going to put on ourselves is we're going to say, well, this encoding vector, this preferred direction vector, this thing which indicates what this neuron likes, we're going to constrain that to be a unit vector, basically because that's going to mean this term in the similarity disappears. That's also got a really nice side effect, because that means in the scalar case, in the case where there is just one dimension being represented, well, there's only two unit vectors, +1 and -1. So this becomes exactly what we were saying here, of just multiply by 1 or -1. Okay, so this is just a special case of our multidimensional version. Okay, that should be confusing and weird. Let me try nailing that down a little bit more. This is not an easy concept. This is not how people tend to think about neurons representing information, because we're so used to drawing curves this way. So what happens with these sorts of curves the moment you say, okay, hey, there's multiple things being represented? Okay. If I want to make this plot, but with multiple things being represented, well, now I suddenly need to make this a 3D plot where I've got two different things varying on the bottom, and then I've got this activity curve showing at the top. So that's what we're plotting a fake one of those here. Okay, so this is the various different things that this neuron might be sensitive to. Okay, across these two directions. And then what I'm plotting, this little curve here, is this neuron's response. So what is the activity of this neuron? Okay. And we are just using this equation. We're saying, all right, this neuron has some preferred stimulus. This is the EI. We're multiplying by some gain value. We're adding some bias value, feeding that into current into a leaky integrated fire neuron. But now we're just plotting what that looks like when we've got a two-dimensional input. And it's going to look like this. Depending on your neuron model, this curve is going to be different. This orange line here that's sort of pointing off in this direction, that's going to be the direction that this neuron is most sensitive to. and this neuron is most sensitive to this particular direction in the 2D space. Okay. But in practice, when if there's a real neuron doing this in the brain, it's going to be really hard to sample every single one of these points and see how the neuron responds, right? Because this would be, I'd have to vary things. I'd have to, provide the neuron this stimulus, see what the activity is. Provide it this stimulus, see what the activity is. This one, this one, this one, this one, this one. There's tons and tons and tons of points here. I'd need to try a whole bunch of them, find out what the activity of the neurons are in order to make this sort of plot. What our claim is going to be is that in practice, people tend not to do that. They intend to sort of, well, I can't sample this whole space. I'm going to do something else. One thing that you might do is sample, say, around this dotted line. So only sample the points on this unit circle. And if you do that, you get this sort of tuning curve. Okay. So if the only thing I do is I'm varying around this dotted line, then I'm going to get activity that looks like this. And now we have exactly the sort of thing that we were looking for. Okay. Say that again. So this is our equation. And this is going to be an equation that's going to come up over and over and over and over again in this course. So this will be our main, this is how our claim of how neurons are encoding information. We're saying there's some underlying space X. And at any particular point in time, I have some particular neuron. That neuron has some preferred direction in that space. The dot product of X with that preferred direction times some gain plus some bias. That's the total current being fed into the neuron. Then we find out what its activity is. Okay. And if we do that sort of trick, if we have this sort of higher dimensional space, then we're perfectly fine getting these sorts of tuning curves. Okay. The only claim that's going on there is the only trick we have to do there is we have to say, well, look, this X, the space that these neurons are representing, is not a scalar. Okay? It's some higher dimensional space that this value is embedded in. All right, that's a little weird. Fine. Hopefully we're kind of okay. Is there anything else I want to say about that? The core point I want to say is the only thing I wanted out of this whole process is I want some way of mapping from some vector X, okay, into neural activity that I can write down with fairly simple math terms and that can work for any neuron model. Okay? And that's what we're claiming this is. Oh, and, sorry, I don't want just to be able to do that. I also want to be able to make sure that the behavior that I get out of this equation can look like real biology. Okay? If we have some particular real biological system that I really want to, if I know, oh, hey, look, here's some biological system, here's some neurons, here's what their responses are. I could use what we've talked about here in order to find, well, what's a particular encoder, what's a particular AI, what's a particular space X, such that we can make that work. In general, as long as you're willing to make this sort of extra step of saying, all right, maybe we're using a different space than we thought we were. Maybe we weren't using a one-dimensional space, we're using a two-dimensional space. If you allow yourself to do any mapping like that, then yes, you can map any neurobiology situation. In practice, it's going to turn out that we generally don't need to do anything particularly complicated for mapping. We generally just sort of, okay, just add an extra dimension or something like that. And we can go ahead and make lots and lots of different real biological values map into this sort of equation. We're going to come back to that over and over and over again. You're going to have to implement this yourself. Hopefully it'll make more sense once. I mean, that's going to be sort of assignment 1. Is one of the parts of that is going to involve you implementing this and making sure this this sort of trick works, and trying to find gains and bias values in order to make different sorts of neural properties. So there's going to be plenty of time to sort of go over that in lots of detail. But that's our core idea for encoding information. What about decoding information? Because that encoding is really, really constrained by, look, we go and observe the biology. This is what we see. We need to make sure that this system here is complicated enough to match whatever it is behavior that we actually see. So it's some complicated nonlinear process. But hopefully we haven't made it too complicated. It's sort of, all right, it's some dot products, it's some multiplying, it's some adding. Fine. We can encode information. What can we say about decoding information? Because we want to be able to take in, here's some neural data, feed it into some neurons. Fine. We can get some neural activity out. Can we then do anything with that neural activity? And the simplest thing that we might want to do to that neural activity is take the activity and figure out what the heck X was. So we want the approximate inverse of this thing that we've done here. And we're going to put on this extra constraint on ourselves. We're going to say, well, okay, look, you could do something incredibly complicated here. We're going to put an extra constraint on ourselves. And we're going to say, well, what is the best linear decoder? So I want to take my activity. I want to, so this is a bunch of neurons. They have some activity. I want to multiply that by some matrix and have that give me my estimate of X. Why do I want to do this? There's tons of other computations I could do here, right? Why this one? The reason is going to be, again, I want to start with as simple as possible and only add complexity when I need to. Okay. And it's going to turn out that as in general in a lot of math things, when you keep things linear, there's a bunch of nice math tricks that we can end up doing. Right. So again, we've got this general basic idea of let's keep things as simple as we can. This equation up here is as simple as we can make it and still have the mapping between the value being represented and the activity being something that looks like, vaguely like the real system. For this one here, well, this is just the simplest decoding that we can think of. There isn't really it's going to be hard to compare that to a real system. The closest we might be able to do is something like, well, hey, if we can have some measure from the biological system, how accurately it, represents its location, or how accurately it remembers information, or how accurately it represents things in the visual field. Maybe there we could do some sort of thing, some sort of way of finding, is this linear thing good enough, or do we need something more complicated? Spoiler for the rest of the course, we're going to stick with this linear thing. This linear thing is going to turn out to be incredibly powerful, and there's very little evidence that we would need to go more than that. All right, but if we're going to go with some linear decoding here, we're going to have to just take this activity, the activity of a bunch of neurons, multiply it by some matrix, and we want that to turn into, well, what's our original value? What's the value being represented? How do we find this decoder? Well, if we just go talk to our nearest mathematician, they would just look at us and go, well, this is why we invented least squares minimization. Right? What we're saying here is, well, look, if you want to find the best D, first thing you've got to do is you've got to decide, all right, is it across all values of X? What's the range of X? Does X go from -infinity to +infinity? Does it have some smaller range? Give me some limits on bounds on this range of X. Okay. So that's our, and what we, so that's this big capital X thing. I want to make sure that across that whole region, the error, which is the difference between x and the decoded value of x, so this is, x is there, that's the decoded value of x. So x gives us our activities, activities times something gives us our decoded estimate. I would like that difference to be small, so please minimize this across that whole space. Okay, so we pick some space that we're going to be optimizing over, and we are going to, we want to minimize this difference. Okay. There's a bunch of fun math that you can do there. In the notes, we explicitly point out that math. In fact, I think I'm going to show that just to actually really force people to note to people that, hey, in addition to the slides in this course, there's also some really good notes that were written by Andreas, the person who taught this course last. So they're also linked. So every single one of the lectures also has some notes here. And they basically go through the same content that I'm pointing out here, but in sort of a more text form. If you want the particular derivation of least squares minimization, then we can actually go ahead and do the math of, all right, you write down what that difference is, the magnitude of the difference is. You go ahead and say, all right, this is the thing I want to minimize. Because you know that it's a quadratic equation, then you know that it has one minimum, or sorry, one extremum. So that's going to mean that all you have to do is you take its derivative and you set the derivative equal to 0, and then you solve. Okay. So we go through that process. Notation gets a little bit ugly, but the details are there. I'm going to go back to the actual course right now. One important thing that's going to come out of that, though, is because this is some neuron nonlinearity thing, basically you can't do this analytically. So instead of doing this perfectly across an entire space, we're going to sample this space. So we're going to pick a set of values of x. Maybe we just randomly generate a bunch of points x across the range of x values that we're interested in. For each of those points, we can go ahead and find out what the activity of each neuron is. Right. And what we really want to do is we want to minimize the difference between the decoded value at each of those points and the actual value. Okay, so just turning this integral into some sampled thing. Okay. When thinking about it that way, it becomes a little bit easier to write down because you can write it as in sort of this matrix notation. Okay, so what am I saying here? So let's say I've got a bunch of points that I'm interested in. Okay, and I've got n of these points. All right, and I just have, maybe if I just have this giant list of points, x1 through xn, I'm just going to write that as a big giant matrix x. In general, x, because each of my points could itself be multiple. If x is a vector that's being represented, if it's a two-dimensional value being represented, then this big X is going to be a 2 by n matrix, or n by, 2 by n. I always get which way around matrices are. I always get that confused. So that's going to be our set of points. For each of those points, and each neuron, there's going to be some activity for that neuron. Right. So each of these points, we can find out what the activity of that neuron is. That's going to be a big matrix that is the size number of neurons by number of points. Right. So that's going to be a big matrix. But fine, it's just a big matrix. And we can generate that, like once we have, there's nothing fancy to that. Once we have each neuron's preferred stimulus, each neuron's gain, each neuron's bias, and we know what our neuron model is, right? And we just do this math and we get our activities. So that's going to give us this whole matrix A. Okay. What we would really like to do, so this is sort of another way of doing the derivation that I pointed out in the notes. If you want to write this in matrix form, what you're really looking for is I want to be able to take that activity, take each one of those elements in that activity matrix. If I take the activity, multiply it by the decoder, then I want the result to be the original values. Right? That's what I'm looking for. Right? And the standard way to do that is, I want to solve for D. I can't just multiply by the inverse of A transpose. I can't multiply both sides by the inverse of A transpose, because A transpose might not have an inverse. In general, it doesn't, because it's not a square matrix. So the standard trick in this case is you multiply both sides by A. Right? Now you've got this thing over here, which is a square matrix. Right? That's AA transpose. Right? So now I can multiply both sides by the inverse of that AA transpose. Okay. This thing here and this thing here are now going to cancel out. So now I'm going to get that the D transpose is AA transpose inversed AX3. This is the Moore-Penrose pseudo-inverse, if people have done that in algebra. All right. Some people have the algebra background where that's just blindingly obvious and intuitive. Other people don't. I really want to just point out, like, this is just sort of basically the thing that algebra was invented for. This is so incredibly common. This is what you do with matrices. So this is an incredibly common thing to do. It is built into most matrix. Should be built into any math library. In Python, you can just write it like this, where you have this A matrix, you have this X matrix, and you say, hey, give me the least squares minimum solution for it, and it gives it to you. Okay. So all this is pointing out is this minimization problem we're describing here is a well-described, nice, straightforward one. So, what does that give us? Because at the moment we've got a whole bunch of weird math going on here. So let me try giving a sort of a higher level overview of what we've just done. We have a bunch of different neurons. Okay. Each of those neurons has some mapping from X into activity. Okay. They have all the same neuron model, so they're all leaky integrate and fire neurons, but they all have different gains, biases, and preferred stimuli. So that is, in our math terms, that is each of those neurons have different parameter here, and different here. Okay, and again, each of these parameters does something different. This parameter here is telling me what is the preferred stimulus for this neuron, and since that's sort of the thing that really drives the encoding, that's why we're using letter E for encoding. So this is, what does this neuron prefer? How strongly does it prefer it? And what does it do when it's getting an input of 0? Just what's its background preferring level? By preferring, I'm using this weird terminology of preferring just because that comes out of the neuroscience as well. By prefer, I mean fires more. What sort of things does it fire for? Okay. So what does it prefer, how much, and what does it do just in the background? Okay. If those vary for a bunch of different neurons, then I might have something like this. Okay. Now here is a situation where X is a scalar. It's a single value between -1 and 1. Right? And if I just generate a bunch of X values between -1 and 1, feed it into that math, right? Then I might get curves that look like this. Okay. So each of these curves is a different neuron. Another way to think of this is the A matrix that I just talked about generating. Okay, if you just plot it, if you had all those values in a row and you just plotted them, right? That's this A matrix. where I'm just computing the activity for the activity of each neuron for a bunch of different points. That's this matrix. So that's just plotting that matrix. In the special case that it's one-dimensional, and so we can just sort of put all of those points in a nice order. A little place, nice like that. So that's our A matrix. So that's mapping, that's our encoding. We've taken X and we've encoded it into a bunch of neural activity. And now what we're trying to do is do this linear decoder. And so this linear decoder, the whole point of this linear decoder is that I could take any particular neural activity that I'm seeing. So let's say right now I'm seeing this neuron, this neuron, this neuron firing at 80 hertz, this neuron firing at 90 hertz, this neuron firing at 120, this one firing at 150, this one firing at 200. And all the other ones are firing at 0. Right? So at some instant in time I might see that. Whoops. I need some matrix, D, that if I multiply by those values, I get an X value out that is pretty close to 0.8, 0.9, something like that. Okay. And I want that same matrix to work for all the other values, for all the other activities. If I go ahead and do the math that I just showed on the previous slide and then try it out, this is what I get. Okay, again, what we're seeing here, this blue line, that's just the result of computing that math. And then I'm just plotting that represented, that output value. Okay. And this seems to be indicating that, hey, we're doing a pretty darn good job. Matrix inversion works. We have found a decoder for these neurons that works pretty well. If X is 0.8, I get some activities, and I take those activities, I multiply them by D, I get this value up here. And it's like, yeah, that's pretty close. 0.8, 0.8. Ideally, this blue line would be exactly on the dotted line. We're a little bit off. And indeed, we can plot how much off we are. So what we're plotting here, this is the difference between our decoded value and our actual value. Okay. And we're like, oh, hey, yeah, this is pretty good. Okay, that's a little bit weird. That's as far as I'm going to go in this particular part of the lecture. The second part of this lecture, or I guess lecture 4, whatever, this set of slides, the second part of what we're going to go to is going to be, well, hold on a second. This decoding that we're doing right now is assuming some pretty perfect behavior of these neurons. In practice, the neurons are not going to be giving us exactly this perfect average behavior. We want to be robust to that. Okay? Because it turns out if you're not robust to that, very bad things happen. And we would like to fix that and make sure we are robust into it. Okay, so we're going to need to slightly modify what we're doing here. But it'll only be a slight modification. The conceptual aspect that we're doing here of I want to do some encoding of a vector into a bunch of neurons, and do some linear decoding from that neural activity to get that value back out. That we're going to stick with. We just maybe have to be a little bit more complicated about how we're generating D. Okay. All right, I'm going to leave it there, and we will see you next time. Thank you very much.